Hi guys, I'm a radio amateur and recently bought a handheld amateur radio. It's the Wurkkos TS22. After using the radio for 2 days, I noticed that the battery supplied only lasts a few hours. I found this a bit disappointing. After optimizing some settings on the device to save power, the 1800 mAh battery lasts a little longer. But I would still like to have a battery with a significantly more capacity. As far as I know, Wurkkos does not offer such batteries for the FT70D. On Aliexpress I saw a good battery pack that a friend also uses with a nominal 2500 mAh. The link is in the description. That's 39% more capacity, but I want even more capacity. That's why I'm thinking of building a battery myself. That should be possible, right? I have a 3D printer, knowledge of electrical engineering, and manual skills. On Thingiverse, I saw such a battery case for the FT70D with 18650 cells has already been developed. However, I would like to train my 3D design skills and adapt the design completely to my needs. So now I have to spend many hours developing my own casing according to my needs. 48 hours later. This is what the result looks like. Here you can see the base, which will later prevent the radio from tipping over. And here you see the side where the contacts will later be mounted. I've also provided a circumferential groove like with the original battery. Optionally, I could then install an O-ring to keep the case rainproof, but I will not do that for the time being. Here you can see the lid. Since the space in the case is very limited, I made the lid relatively thin, but provided struts on the underside to give the lid mechanical stability. Because I only want to print the housing without the lid for now, I use the Prusa Slicer cut function to temporarily remove the lid. So now I can generate the G-code. Oh no, that's a lot of support material. From my other 3D printing videos, see the playlists, you may already know the organic setting for the support material. Let's see how it looks. Yes, it's much more efficient. If the print works well with this, you will save a lot of time printing material and work with this configuration. So the 3D printing has just started. You can already see the base of the organic supports. Hopefully the print will work without any problems, because the print will take several hours due to the size of the component. In the meantime, we can take a look at the battery cells that I had already ordered. I was looking for renowned 18650 lithium-ion cells with the highest capacity. In the end, I ordered Samsung cells. The model name is INR 18650-35E. The cells have a nominal capacity of 3500 mAh. This means an increase in capacity of 95% compared to the original battery. Let's see what wattage the cells have. Oh, good. The wattage of both cells is identical and in a good range. That's good and important because the cells will later be connected electrically in series. For this, the cells have to be almost identical. Look, the housing is finished printing. The surfaces look nice and smooth. The supports obviously worked well on the overhang. Nothing is sagging here. Now I can remove the support material and threads quite quickly. This support was really easy to remove. Fascinating that the printer can even print such slim, freestanding structures. Let's see if the battery housing now fits into the radio. Oh, the housing doesn't click into place completely. Why? Apparently, the barb on the housing is set a little too high. But I might be able to solve the problem with the carpet knife. I will just cut a little off the barb at the top. Now it's getting exciting. Let's see if the housing clicks into place now. Yes, it works. Then I just have to adjust the barb slightly in the design later. Let's see if the radio is stable with it. Yes, I can push the device quite far to the side without tipping it over. With the weight of the battery cells, it will be even more stable later. Very nice. But I'm going to quickly adjust the design of the barb. That looks good. Now another 3D print should click into place too. One very important question is still open, namely whether the battery cells will even fit into the housing. As you can see, it fits. The cells even have some play, but only a few millimeters. So the contacting of the cells later has to be done in a way that saves space. But now we are moving on to the next step. I need contacts so that the current can flow from the battery pack to the radio. I want to make them from this nickel-plated steel strip. Oh damn, the metal strip cannot be pushed into the slot. In principle, such a tiny slot is a self-supporting construction. It is quite obvious that this does not work to keep the passage clear during printing. Instead, the printed structure sinks down from above. Let's see if I can push the metal strip through if I heat it up a bit beforehand. Oh man, that doesn't really work well. That also ruins the 3D print as a whole. I really don't feel like doing that. Instead, I'm going to change the design again. Instead of the slots for the metal strips, I have developed a recess for a circuit board strip. This circuit board strip will later have copper fields that match the contacts on the device. I have provided the feed-through opening for the electrical cables with an intermediate bridge. Then the printed structure shouldn't sag. I also provided a groove on the inside of the housing so that the wires don't protrude into the space and the battery cells fit really easily. The 3D print is now finished. The design for the feed-through opening obviously worked. Now comes the mandatory program again, removing the support material. And now the assembly attempt. Will the housing now snap into place without modification? Yes, it works without any problems. And the print quality and detail is again very good and durable. If you're interested in which 3D printing material I use, I will put a link in the video description. In the next step, I want to make the contact board. Here you see the raw version. Let's see if the arrangement of the contact surfaces matches the original battery. That looks good, but the board still needs to be trimmed slightly. And the holes for the connecting wires still need to be drilled. One hole is not in the middle, but that doesn't really make any electrical difference. In the next step, I have to solder the connecting wires. Now that the contacts are mounted, the next step is to mount the other components. battery cells absolutely need a BMS protection board. This protects the individual cells from damaging operating conditions. If you're interested in the details, just watch my video about this BMS board after this video. You can find the link in the video description. These are narrow and flat. This means I don't have any space problems because space is extremely tight. The board fits well between the two cells. To double the insulation of the sheet metal tabs on the top, I mount insulating tape underneath. Since the BMS board also needs an additional buffer layer, I also put a strip of insulation tape underneath. The BMS board has 3 connections for the batteries: plus, minus, and the middle contact. Now the positive and negative poles still need to be wired. This is what it looks like in detail now. Here you can see the connections for the load. In order to keep the wiring paths with the thin copper enamel cable as short as possible, it makes sense for this end to point towards the contacts on the housing. Let's see if it still fits into the housing. It fits like a glove. Now I can solder the plus and the minus cable. My battery cells can be charged in a temperature range of 0 degrees Celsius to plus 45 degrees Celsius. Okay, I haven't found an available NTC resistor that would have the right value at the temperature limits mentioned above. But honestly, I always charge my device at home, and it's usually around plus 20 degrees Celsius here. So I can just solder in a 12 kilo ohm fixed resistor as a makeshift solution. And that's exactly what I'm doing now. To ensure insulation from the circuit board, I stick a piece of polyimide adhesive tape underneath. It can withstand up to 260 degrees Celsius and sticks very well. By the way, I also bought the adhesive tape from Aliexpress. So the resistor is mounted. To fix the wires and insulate open contacts, I stick polyimide adhesive tape over them. That looks really good. Now I want to see if the lid fits. Yes, now it fits. I've noticed, however, that the battery cells can still move slightly from left to right. It definitely shouldn't stay like that. You can see the movement here if you look closely. But no problem. I have a piece of elastomer here that's about 1 millimeter thick. It's nice and elastic and will serve as a mechanical buffer. Let's see if it fits. Yes, it fits exactly. But the height isn't right yet. So now it fits perfectly. And the cells can no longer be moved. Now I can mount the lid with a few adhesive dots. To ensure that the lid is pressed down while the adhesive has set, I put this steel plate on top. It is nice and thick and has a lot of weight. To be on the safe side, I put my roll of solder on top. Now the whole thing has to set for a few hours. I finally have a long operation time with the FT70D. What a great success! If you're not already one of my high-valued subscribers, you have now the chance to become one. Give me a thumbs up and a compliment in the comments. I'm happy about that, and the algorithm likes that too. Check out my playlists too. There you will find other interesting videos from me sorted by topic. In the video description you will find the links to the parts I used, such as the 3D printer filament, spot welding board, polyimide film and nickel-plated sheets metal strips. Have a great time. See you next time. Bye bye.